Hello, Sauce here. This is a video lesson reintroducing continuity with a piecewise function. Continuity is a topic in itself. We've had lessons on the concept in the past. Piecewise functions are also a concept in itself with its own lessons to introduce. This is a review of both. I'm going to give an example of a piecewise function. A piecewise function is a function that has more than one expression to find its values, but the expressions are used in a restricted domain. So if I begin to write this piecewise function, I have an expression to calculate values, 1/2 x plus 1, and I've placed a comma. What comes next is the domain values in which I'm going to use that piece. So it's restricted to all values of x that are less than 4. And if x is not less than 4, if we have x values in the domain greater than or equal to 4, we're going to use this second piece, negative x plus 6. This is a piecewise function. I'm going to tie these two pieces together with a set bracket, and I can name this function. It's a single function with two pieces. I'm going to graph. I'm in the habit of graphing each piece as its own expression completely, but lightly, and then darkening that piece with the restricted domain. You'll see me do it. This is a linear piece. It has a slope of 1/2 and a y-intercept of 1. I could use a t-table, but I'm going to use the conceptual approach to quickly graph it. Here I have a y-intercept of 1 and a rise of 1 for a run of 2. I'm going to graph the entire piece very lightly. And the second piece has an intercept of 6 up here and a slope of -1, which I'm going to graph in its entirety there, lightly. I'm going to observe the transition point at 4. I'm going to put a tick mark there, and I'm in the habit of using a soft dotted line, just like an asymptote. It's not a part of a function, but it highlights an important location on the graph of this piecewise function. This is the transition point. It's at 4 where we transition from using one piece to find values to the other. And now that I have both pieces graphed completely, I can very easily see and darken the piece before this transition, which is the linear piece that has a slope of 1/2. And once I get to that transition line, I can switch to where I graphed the second piece and darken the part after the transition of 4, or at 4. And I can clean it up so it's not confusing and erase the pieces that, or the parts and places that I didn't use. And to finish up the graph of the piecewise function, I have to be precise at the transition point, at the domain value of 4, what piece of the function am I going to use to find the value? Well, I'm looking at the symbol that includes the equal to. So this is x is greater than equal to 4. So that's the piece that when I'm using the value 4, I need to put a closed dot because I can be right on that function value. It's helpful for the other piece to have an open dot as a placeholder. Open dot, remember, is all the values up to that point, but not including that point, because on this piece, I'm strictly less than 4, not equal to it. I have a complete presentation of the piecewise function. There's a break right here. It's not continuous right here. And what do we mean by that? Well, let's review the basics of what it means to be continuous. We could ask the question, is the function continuous? And we have a couple of manners of justification. We could justify informally And that's the attitude towards justification that's easy and visual. Can I draw the function without lifting my pencil? If I can, then the function is continuous. I can't draw this function without lifting my pencil. I can start here, and as soon as I get to this transition, I have to lift my pencil to continue drawing. So this function is not continuous. That justification is informal because it doesn't rely on rigorous algebraic methods to formally justify precisely why not. So there is a formal justification. And I won't review it thoroughly right now. We'll review it very thoroughly very soon. But to review what a formal justification requires, very quickly, it requires that at every point in the function, you can show, demonstrate, prove that at that point, there's a value of the function, there's a limit at that location, and the value and the limit are equal. So to review continuity, we need to review limits. But formally, the reason why this function is not continuous is because it doesn't have a limit. It has a value, it's right there. It doesn't have a limit because the one-sided limits at 4 are not equal. So there's no absolute limit. Again, more review on precisely how to state that, and a review of limits will come soon. Why would you use a formal justification when an informal justification will say the same thing? Formal justification is more tedious, it's more work. The reason why formal justifications are something that we want to be able to do, we want to know very well, is because there's more interrelated information in the formal justification. It requires a greater understanding of the related concepts of continuity. And so when we apply the concept of continuity in applied problems in science, because there's more interrelated information, we might be able to see that continuity is an issue or a part of the concept we're working with when we only have a limited amount of information to work with. In other words, we can come at the concept of continuity from many directions with limited knowledge to begin with when we're familiar with and we can apply the formal justification. So that's why we want to learn the rigor. One more thing to say about this. We can ask if a function is continuous on a restricted interval. If we simply ask, is this function continuous? Then we're implying if it is continuous everywhere that it is defined. This function is not continuous everywhere because it's not continuous at 4. But what if we asked if it was continuous and we stated an interval in our question? Continuous on, then interval notation from A to B. Well, informally, if we start drawing the function and we start at A, and all we care about is drawing until we finish at B, we didn't have to lift our pencil, so this function is continuous on the interval from A to B.